Here is a very interesting application of Bayesian inference. So we have a coin and we have infinite patience to toss the coin. So suppose the coin is tossed 10 lakh times, out of which 4,98,800 times we got head and the rest of the times we got tail. So we are interested in the hypothesis that theta is 0.5, where theta is the probability of getting a head for that particular coin. So clearly the null hypothesis is that the coin is a fair coin, and the alternate hypothesis is the coin is not a fair coin. So now, using the usual type of testing, means the frequentist type of testing, the probability you would be interested in obtaining the probability that if I have a fair coin, what is the probability that I would get 4,98,800 heads. So if this probability is less than 5%, then the hypothesis that the coin is fair will be rejected. So this is the frequentist approach. Now let us see how Bayesian approach works. So suppose that now in Bayesian approach, we must have prior distribution of theta. So now because we are interested in testing the hypothesis, so we don't exactly need prior distribution for theta, but it is enough to have prior probabilities associated with the hypothesis. So suppose before conducting the experiment, that is before flipping the coins, we assume the coin to be fair. So the prior probability of the hypothesis, that is H0 and H1, will be 0.5. Now suppose we have conducted the experiment and we have got the data. The data is nothing but the fact that we have got 4,98,800 4,98,800 hits out of 10 lakh tosses. So we use this information to get the posterior probability of both these hypotheses H0 and H1 using the Bayes theorem. So now this probability of D given H0 in this is obtained by assuming binomial distribution for the data. Here D represents the data, that is the fact that we have got 4,98,800 heads. So what is the chance that this will happen if the coin is fair? So it will be simply n choose D, where n is 10 lakh, D is 4,98,800, 0.5 raised to D, 1 minus 0.5 raised to n minus D means simply 0.5 raised to n, where small n is 10 lakh. Similarly, the probability that we will get 4,98,800 heads given that we are dealing with an unfair coin will be, now you will have to integrate this. So n choose D, theta raised to D, 1 minus theta raised to n minus D. Okay, so this can be uh, derived like this. So n choose D beta into beta integral with these parameters. So using all this, we get the posterior probability of H0, which is approximately equal to 0.98. Now notice that this is a really large probability. So it clearly indicates that when we assumed equal chance for null and alternate hypothesis, then after getting the data, the chances of null hypothesis increased from 0.5 to 0.98. And so it clearly indicates that the data supports the null hypothesis. Very well. Now let us consider the frequentist approach. Now, as we have stated earlier, we reject H0 if there is less than 5% chance of getting the number of hits which we have actually got. So we assume that the data are normally distributed because the sample size is really large. So 10 lakh. So this is the natural assumption which we get after applying the central limit theorem. So the p-value of the hypothesis, null hypothesis, comes out to be 0.01639, which is less than 2%, because the chance that we get these many number of hits is small, and so we have got the p-value to be really small, and so we end up rejecting the hypothesis. So even though intuitively we do feel that we should have accepted the hypothesis of having a fair coin, we end up rejecting it if we apply the frequentist approach, whereas we take the right decision if we apply Bayesian approach. So this is how the Bayesian inference makes a difference when applied in appropriate manner.